Hey everyone, good morning all of you. Welcome back again to our NEET Bridge course for NEET 2026. So till now we have discussed a lot of fundamentals, especially emphasizing on the unit of kinematics. But every time I tell you the same thing, that whatever you are learning these days in these fundamental topics, this is not restricted only to the unit of kinematics or mechanics, but that will also keep coming in different chapters and units of physics. All right. So we have discussed a lot in motion in a straight line, motion in a plane. Yes, of course, I didn't complete the entire unit because this is a bridge course. Here we are going to discuss the basic fundamentals which will be helping you in strengthening your physics, strengthening the maths involved in physics, and also we will be discussing the predictable models. So every time in every session I take it as an opportunity to discuss one or two models every time that has a probability to come in the NEET 2026 exam. All right. With that enthusiasm only, we are going to discuss a new topic today, and we are starting with a new unit of Newton's laws of motion. All right. So the topic of our discussion is conservation of linear momentum. That is from Newton's laws of motion. Yes, this conservation of linear momentum is out of the 4 fundamental conservation laws which are applicable in physics. The first one is conservation of mass and energy together. Okay. Next is conservation of charge. Next is conservation of linear momentum. And the last one is conservation of angular momentum. So today we are going to discuss conservation of linear momentum, when it is applicable, how we should apply that, what are the fundamental models which are there, and what are the critical models which are there. And in today's class, we are going to adopt the paternalistic way, which means the pattern-based way of learning. Very soon you will find me solving a lot of models in front of you, but every model will have a common pattern. If today you understand that common pattern with me, then definitely where your rest of the competitors may be able to solve the question, but by conventional long methods, we will be having our own short way, smarter way of doing the same problems. Okay, so are you prepared? Hello, hi, good morning. Good morning, Neharika. Good morning, Sadvik. Okay, so let me take you towards the concept first. What is the concept here? See, we know as per Newton's second law. What is Newton's second law? Newton's second law says, Newton gave 3 laws of motion. The first one is law of inertia. An object will continue its state of rest or motion until or unless an unbalanced external force is applied on it. Newton's third law is action-reaction. For every action, there is an equal and opposite reaction, and these action and reaction act on 2 different bodies. And the second one is this one. It says the time rate of change of linear momentum of an object is directly proportional to the external force applied on the body, on the object, which means indirectly it is also called as real law of motion, because Newton's first law and Newton's third law can be deduced on the basis of Newton's second law. We can see that also. But here our concern is Newton's second law. What exactly it says? It says that a body's or a system's linear momentum can be changed only after applying an external force on it, which means if there is no unbalanced external force, acting on the system, then you can't change the linear momentum of the system. If there is one force acting on the system, then definitely system's linear momentum can be changed, will be changed. If 2 or more forces are acting on the system, then whether the momentum will change or not, that will depend on whether the forces are balancing each other or not. If the forces are balancing each other, there is no net force, which means there will be no change in linear momentum. And if the net forces are not balanced, like the net force is an unbalanced force, which means a non-zero force, then the role of that force will be to change the linear momentum of the system. Okay, so if there is a non-zero force, that will change the linear momentum of the system. If there is no unbalanced force acting on it, the system's linear momentum will be conserved. That is the principle of conservation of linear momentum. सही है. So Newton's second law is, according to Newton's second law, we say that time rate of change of linear momentum of an object is the external force applied on it. So external force is equal to dp by dt, dp by dt here. If particularly I say the external force acting on the system is 0, if external force acting on the system is 0, in that case, then can I say the linear momentum dp by dt is equal to 0, which means, see, we know that constant differentiation is 0. So if the derivative of linear momentum is 0, which means the linear momentum doesn't change with time, it is constant or conserved. Now the meaning of constant and conserved, is that same, sir? No, it's not at all same. So what I want you to understand is that here, if external force acting on the system is 0, then the system's linear momentum is going to be conserved. This is called principle of conservation of linear momentum. Conservation of linear momentum. Okay, very simple. Very simple, principle of conservation of linear momentum. Before I talk further, I would like to emphasize on this point that if a physical quantity is constant, then you can say it is also conserved. But if a physical quantity is conserved, that doesn't imply that it is constant. I repeat, constant means what, sir? Constant means it is not going to vary throughout. Conserved means what, sir? Conserved means that initial value must be equal to final value. All right. So if something is fixed, if something is constant or something is fixed, then obviously its initial and final value will be same. But vice versa is not true. Reverse is not true. Means there is a physical quantity whose initial value matches with its final value. But who knows? It may vary in between. All right. So if initial and final are same, that doesn't mean it has to be constant. It may vary in between. So conservation doesn't imply being constant. But if it is throughout constant, then obviously its initial and final values are going to be same. So constant means it is going to conserved also, but conservation doesn't imply that the physical quantity is constant. Now, trying to relate it here, if external force is 0, means linear momentum's derivative is 0, and if differentiation or derivative is 0, the physical quantity is constant. Since it is constant, you can safely call it conserved also. And hence this is called as principle of conservation of linear momentum. I hope this logic is clear to you. Okay, principle of conservation of linear momentum here. Right? Now, for example, one basic example I will take here. That suppose there is a system, like there is a body A and there is a body B. They are interacting with each other within a system. So suppose there are two masses, MA and MB, and they are attracted towards each other, or there may be two charges which are attracting or repelling each other. So it is experiencing a force F acting on A due to B. F acting on A due to B. And this is also experiencing a force, say attractive only. This is F on B acting on B due to A. I can use other symbolic notations also for this, but right now I'm clearly writing everything for you. That there is a force acting on A due to B. There is a force acting on B due to A. If this is a force which is acting on A, so you need to keep your pen on A and show its direction. If that's the force which is acting on B, then you need to keep it on B and show its direction. Now, what this will do? This force will change. It is changing the linear momentum of A. So the unbalanced external force acting on A will change the linear momentum of A. This force is changing. This is an unbalanced external force acting on B. So it is changing the linear momentum of B. It is changing the linear momentum of B. But if you consider this entire one as a system, let me show this to you here. If I consider this entire one as a system here, then on this system, the external force acting is 0. If the external force acting is 0, this implies system's momentum, which will be given by the sum of linear momentum of A plus linear momentum of B, that is going to be a constant or conserved. Are you getting it? What I'm saying? So basically, if we consider only A as a system, then there is some external force acting on A which will change the momentum of A. If we consider only B as a system, then there is some external force on B which will change the momentum of B. But if you consider both as a system, then their mutual force has become an internal force. Then their mutual forces have become internal forces. There is no external force acting on the system, and the linear momentum can only be changed by external force. The linear momentum can only be changed by external force. Internal forces don't have the capacity to change the linear momentum. I repeat, internal forces don't have the capacity to change the linear momentum. Okay, so if I take it further here, okay, so how this external force is 0, I would like to emphasize that also. How this external force is 0 as FAB vector and FBA vector acting on A due to B, acting on B due to A will become internal forces. Now what do you mean by these external and internal forces, sir? Internal forces are the forces which exist mutually among the parts of the system. Means if your system is the big one, then A and B will be considered as the internal part of the system, and any force of interaction they mutually have, that will be called as internal force. That will be called as an internal force. As we can see, these forces are obviously equal and opposite, and I have indirectly followed Newton's third law also diagrammatically, that these are equal and opposite. All right, so they will nullify each other. External force will be definitely 0, and hence the linear momentum of the system will be conserved. All right, not only that, if I take you further from here, so can I say here final momentum of the system must be equal to initial momentum of the system. Final momentum of the system must be equal to initial momentum of the system if both objects are starting from rest. In that case, what we can write, see, I'll do it for you here. Okay. So if both objects are starting from rest, then can I say your final momentum will be MA VA vector plus MB VB vector, and that will be equal to 0 vector. Why 0, sir? Because they are starting from rest. If they are starting from rest, which means initial momentum of the system is 0. That's why final momentum total final momentum must be equal to total initial momentum. Once again, who has the capacity to change the linear momentum of the system? Only external force. If there will be an external force, then definitely you will change the linear momentum in that direction. You may change the linear momentum in that direction. When to and when not to, those will be different cases. Today, we are not talking about the variation of the momentum. Today, we are talking about the conservation of the momentum, for which the condition is that there should not be any unbalanced external force. There should not be any net force on the system. All right, internal forces may be there, but they don't have the capacity to change the linear momentum. All right, now if initial momentum of the system is zero, I mean, if the particles of the system are starting from the rest, then initial momentum will be definitely zero. According to the conservation of momentum, if final momentum is to be made zero, by initial is zero, if you want to make the final momentum also zero, and there are two objects, then obviously they must be having equal and opposite. So MAVA vector must be written as MAVA vector must be written as minus of MBVB. What is this minus sign showing? Minus sign is showing that they will gain the momenta in the opposite direction. I hope that is clear to you. All right. So that is the entire situation in front of you, in which an interesting part we still have missed. That is, if overall external force acting on the system is non-zero. Okay, I would like to attach that also. I would like to attach that also as an important point for you. Okay, so here, see, I am attaching another point. I am saying if external force acting on the system overall, if external force acting on the system overall is non-zero, then we can't conserve the linear momentum overall, but or you can say such that external force in the vertical direction is non-zero and external force in the horizontal direction, x-axis, is zero, then we can still conserve. See, conservation of linear momentum is a very important tool. It's a very important technique to solve the problems. So basically, we want to apply the conservation of linear momentum. We want to use it as a technique. Now the situation is, sir, when you are allowed to use the conservation of linear momentum as a technique to solve the problems. Okay. So in that case, I would say that if overall external force is zero, then naturally overall you can conserve the momentum. But interestingly, in some problems, overall external force is non-zero, but in a particular direction, say along the inclined plane, say along the x-axis, say along the y-axis, depending upon the problems or situations, in a particular direction, the net force will be zero. Then we will be happy to apply the conservation of linear momentum in that particular direction only, which means we can still conserve the linear momentum. We can still conserve the linear momentum along x-axis. That is, if external force acting in the x direction is zero, then we can always apply the conservation of linear momentum along the x-axis, or final momentum vector along the x-axis must be equal to initial momentum vector along the x-axis. Since you are talking about the x-axis, the convention to be used here is forward must be taken as positive, backward must be taken as negative. And in y-axis, we all know upward will be taken as positive and downward will be taken as negative. That is the situation. Understood? To hear what we have learned, that only external forces have the capacity to change the linear momentum of the system. Choice of system is very important task. Choice of system is very, very important. Now, how to choose the system? In rough language, in rough terms, I would say that, roughly, I would say that we will prefer to choose the system as large as possible. When I say as large as possible, my concern is not with the size of the system. My concern is with the fact that more number of forces, if I can consider them as an internal, which means either there is no external force acting on the system, or at least in a particular direction, in a specific direction, there is no external force on the system, so that if overall there is no external force, we can conserve the overall momentum vector of the system. Or else, if the external force in a particular direction is constant, we can conserve the linear momentum in that particular direction. I hope the logic is clear. So choice of system is very important, and regarding the particular direction conservation of linear momentum, that is also in front of you. Any doubts till now? Any doubts? No? Okay, chaliye. Let me give you some models of comparison, like how to apply the conservation of linear momentum. I'll give you two models. Generally, I call it a 9th class model and a NEET model. One is the 9th class model, one is the NEET model. Why do I say that? Because one fundamental model is the one in which you can apply the conservation of linear momentum while writing m1v1 equal to m2v2, and all the velocities and motion is to be considered with respect to ground. Okay, you are an observer. You can see a system which was initially at rest. Now the system is breaking into two parts, that is moving in opposite direction as per this conclusion. So opposite direction, m1v1 will be equal to m2v2, end of story. That's what you have written, here. m1v1 equal to m2v2 in opposite direction. All right. Another model which I generally, so this was the model which I commonly call it as a 9th class model. Gun firing off a bullet from the gun. I'll show you that. Another crucial model is, situation will be still the same, but the velocity of one of the particle will not be given with respect to ground. Rather, the velocity of one of the particle will be given with respect to another particle. I repeat, velocity of one of the particles will be given with respect to another particle. For example, the bullet's velocity with respect to ground will not be given. What will be given is the muzzle velocity. Muzzle velocity is the velocity of the bullet with respect to gun. I repeat, muzzle velocity is the velocity of bullet with respect to gun. Then what to do? Okay, let's compare the models. So here one is the basic model, here one is the relative motion model. So the basic model I'm starting with, I'm saying there is a gun, okay, and there is a bullet inside the gun. There is a bullet inside the gun, and initially the system is at rest. Initially, system is at rest. All right. Now, finally, what is happening? Firing happened. Firing. You fired, right? So what will happen? That the gun, say of mass capital M, experiences a recoil velocity. Recoil velocity. Okay, experiences a recoil, gains a recoil velocity, and the bullet of mass, say m0, is fired with a velocity of v0. Okay, so in all such problems, generally what examiner is asking you is the recoil velocity of the gun, which means you will have a gun in your hand, you'll fire the bullet, you know the velocity of the bullet, you know the mass of the bullet, you know the mass of the gun. Examiner is asking you the recoil velocity. Suppose the target is recoil velocity. Determine the recoil velocity of the gun. Recoil velocity of gun. All right. Suppose that is the basic problem model. I generally call it a 9th class model. Why? Now, when you have fired the bullet, so there is a small hammer. I hope everyone knows that there is a very small hammer inside the gun that hits the bullet. All right. Very strong spring action there. So when it hits the bullet, bullet experiences an external force. So see, bullet's momentum is changing because bullet was initially at rest and now it is moving, which simply means bullet's momentum is changing. Similarly, gun was initially at rest and now it experiences a recoil, which means gun's momentum is also changing. So if you consider bullet as a system, there is an external force applied by the gun, which will change the momentum of the bullet. If you consider gun as a system, there will be a reaction force offered by the bullet, which will change the momentum of the gun. If you consider gun plus bullet as a system, then these two forces will become internal forces. There will be no external force acting on the system. So what I'll do over here is, I will say here, system will be bullet plus gun, M naught plus gun, okay, capital M. All right. In that case, external force acting on the system is 0. External force acting on the system is 0. That means the final momentum of the system must be equal to initial momentum of the system. Okay, for the system. And what is the system? That is in front of you. So finally, what is happening? Finally, the gun is moving in the backward sense. So I will write mass of gun into velocity of gun vector plus mass of bullet into velocity of bullet vector. And initially the system was at rest, right? Initially the system is at rest, so initial momentum is 0. What is the mass of gun? Capital M. According to the convention, since you are dealing with the vector quantities and this is the first time, I'll write everything in detail along with their plus minus sign. So this recoil velocity is towards left, so that will be minus of VR plus mass of bullet is M naught and its velocity is given as V naught and that is equal to 0. So from here, the negative term you will take on that side and VR will be equal to M naught V naught by capital M. M naught V naught by capital M, that's your final answer. Alright, very simple. M1 V1 equal to M2 V2. Rest of the things I deliberately wrote theoretically. If it comes in the exam, then in one final step you can directly get the answer. Right now I am teaching everything in detail, so writing everything theoretically. But this is a very simple model or a very short approach to solve this problem. Alright. The critical thing arises when they don't give you the velocities with respect to ground, but they talk about the relative motion. Means they will give you the velocity of the bullet, but that velocity will be the muzzle velocity, which means you don't know what is the actual velocity of the bullet with respect to ground, but you know that what will be the velocity of bullet with respect to gun. I repeat, how does it make the situation different is a very small logic, very small reason that here you are applying the conservation of momentum with respect to ground and everything was given with respect to ground. Every velocity was observed with respect to ground. Here again you will conserve the linear momentum with respect to ground, but the velocities given in the question will be with respect to each other. Those will be the relative velocities. Conservation of linear momentum must be applied with respect to ground only, but the velocities given will be the velocities with respect to each other. Then what to do? So here if I talk about relative motion model, there is this gun having a tiny bullet inside it, suppose, and initially the system is at rest. Again the same situation, initially system is at rest. Why I am writing it again? Because I want you to compare these two situations. Now you fire it. If you fire it, they are asking you, this is mass M, they are asking you the recoil velocity. Obviously this recoil velocity is with respect to ground, because you are a person standing on the ground, your hand or your shoulder experiences a recoil, and you are a person standing on the ground, so this recoil velocity is supposed to be obtained, supposed to be calculated with respect to ground. And this bullet which you have fired, M naught mass, is moving with a velocity V naught, but this time this velocity is mentioned in the problem as muzzle velocity. This is mentioned as muzzle velocity. Now what is the muzzle velocity? Muzzle velocity is the velocity of bullet with respect to gun, which is a moving gun naturally now, because it is also experiencing a recoil now. So with respect to gun, that makes the difference. You will apply, you still want to apply the conservation of linear momentum because the external force acting on the system is 0. And you still want to apply the conservation of linear momentum with respect to ground, but the velocity given to you over there is velocity with respect to gun. All right. So let me write it here. How to solve it? I will say mass of gun into velocity of gun with respect to ground finally, plus mass of bullet into velocity of bullet with respect to ground finally, and that will be equal to initial momentum of the system, that is 0. Initial momentum of the system, that is 0. I want you to understand here, what I want you to understand here is that we are applying conservation of linear momentum is applied here with respect to ground. So if you are applying it with respect to ground, then definitely all the velocities which you will be writing will be with respect to ground. But issue is that the given data is not with respect to ground. Then what to do, sir? Relative motion it is. Don't worry, just listen to it. Just see what I am doing, and then I'll tell you the patterns of doing all such problems. So here, mass of gun will be capital M. Velocity of gun with respect to ground will be the recoil velocity, and that will be minus, or let me write it like this only, that it is a recoil velocity vector, okay, with respect to ground, plus mass of bullet is m0. Now velocity of bullet with respect to ground can be written as velocity of bullet with respect to gun plus velocity of gun with respect to ground, or this is also called as recoil velocity. Okay, that must be equal to 0. I hope this is clear to you. See, what I am telling you is that mass of gun you have substituted, velocity of gun with respect to ground is recoil velocity. You want to write the velocity of bullet also with respect to ground, which was directly given in this case as V0. But here, velocity of bullet with respect to gun plus velocity of gun with respect to ground. You remember relative velocity topic? And don't worry if this equation seems bigger to you. Very soon, in next few minutes, I'm going to give you a very nice logic, very nice trick to solve all such problems. Just listen to it carefully to, boost up your fundamentals. So this is mass capital M. The recoil velocity vector is minus of VR plus m0 as it is. Velocity of bullet with respect to gun. Velocity of bullet with respect to gun is the muzzle velocity, that is plus V0, plus velocity of recoil will be minus VR, that is equal to 0. So if you look at it carefully, you'll have minus of m plus m0 into VR in both terms, or let me just open the bracket, minus mVR minus m0 VR plus m0 V0, that is equal to 0. This implies you can write this VR as taking the negative terms on that side, isolating the VR. You get m0 V0 by capital M plus m0. m0 V0 by capital M plus m0. Now if you look at it carefully, this is the velocity of the gun, for gun. This is the velocity for the gun, and this mass is of bullet. This is the velocity of the gun and this is the mass of the bullet. So can we conclude that here m1 v1 equal to m2 v2, but here you have to always take the opposite mass. I repeat, here you have to always take the opposite mass. Always take the opposite mass. Let me introduce that once again in front of you. Special focus on two particle system. Special focus on two particle system. Illustration 1. Always take the opposite mass. Two particle system. Always take opposite mass. Always take opposite mass. Okay. Remember the rule. How? Illustration 1. Example 1. I will take the same model once again, but not doing this much big. I will say that there is the gun, mass M, inside it there is a bullet which will be fired very soon, initially at rest. Situation is initially at rest. I mean, this trick is applied only if the system is initially at rest. Finally, what is happening? This gun, mass capital M, experiencing a recoil velocity. This bullet, m naught mass, it is moving with v naught. That v naught is the muzzle velocity. Because sir, if those are the individual velocities with respect to ground, then we will use this 9th class logic, which I am saying. Why I say it 9th class? Because it's a very easy one, right? Fundamental logic M1, V1, M2, V2. And generally in different boards, CBSE, ICSE, and like these things you discuss in your 9th class. Okay, then in 11th class, and then obviously for the NEET exam we are preparing. So this one is the basic one. In the entrance exam, in the NEET exam, you can expect this much, but this seems very bigger. So I'm going to give you a shortcut over here. The rule is always take opposite mass. So our way of doing it will be, if here they are asking you that tell me the recoil velocity or tell me the final velocity of the bullet with respect to ground. So here I will say that final velocity, if they are asking you the final velocity of gun with respect to ground, which is also called as recoil velocity. Final velocity of gun with respect to ground, which is also called as recoil velocity. See, since it is in left and I'm writing vector, here I have just calculated the magnitude, so no plus minus. But here, if I'm writing the vector diagrammatically, since it is moving left, I have to put a minus sign over here. Okay, and then I will say always take the opposite mass. So whose velocity you are writing? Gun's velocity. So whose mass is to be written? Bullet's mass. So that will be m naught into the relative velocity. The relative velocity is v naught. Muzzle velocity is actually the relative velocity here. Muzzle velocity is relative velocity. So always take the opposite mass by total mass of the system. M naught plus capital M. M naught plus capital M. Once again, I'll be writing it here that this minus is only because of the direction. Suppose I want to write the velocity of bullet with respect to ground. Remember dear that the velocity given in the diagram is not the velocity with respect to ground. It is relative velocity with respect to gun. So if you are interested in writing velocity of bullet with respect to ground, see diagrammatically bullet is moving in the forward direction. So you should be writing it as plus. Then you will say that here, since you always have to take the opposite mass, whose velocity you are writing? Bullet's velocity. So whose mass is supposed to be taken? Gun's mass, capital M, into relative velocity v naught by m naught plus capital M. M naught plus capital M. I hope you understood. Always take the opposite mass. What is this? Negative sign signifying left. Left. What is this positive sign signifying? Right. Okay, so positive and negative for a vector, that doesn't contribute in its magnitude. It contributes only in its direction. I hope that's okay. All right. Now let me give you another common model here. This model is this model for us is man plus boat. Man plus boat. I hope you are understanding that in NEET exam we will get conservation of linear momentum models, but not with respect to ground. We can't expect this model. It's very rare to come. What we can expect is this model in which they will club conservation of linear momentum with the relative motion, for which for two particle system, I'm giving you a shortcut. If the system contains two particles and initially the system is at rest, then while writing the final velocities in terms of relative velocity, always take the opposite mass. Let us take another example. We have a plank over here. We have a plank over here and or boat over here, which is over the ground, over the water. This boat is of mass capital M. So water will offer negligible external force here. There is no external force acting. Okay, just like gun plus bullet, there is no external force acting on the system. Only internal forces were coming into the picture. Here in illustration 2, what is happening is that there is another person of mass m naught, and initially the system is at rest. Definitely, if the person wants to move over this boat, there must be a friction. Without friction, the person can keep doing the moonwalk, but the person cannot move further. I hope you understood this. If we want to walk over a surface, there must be a friction there. Okay. But interesting part is that friction is an external force on the shoe of the man, on the foot of the man. So man's momentum will change. That friction will also be acting on the surface of the boat. So boat's momentum will also be changed. But if you consider man plus boat as a system, the same friction will become an internal force. It is rough. Here friction becomes an internal force. Here friction becomes an internal force if system is man plus boat. System is man plus boat. Okay, so friction will become internal. All right, and that is every time good for us. Why, sir? Because internal forces, as I am telling you again and again, they don't have the capacity to change the linear momentum of the system. So if all the forces involved are internal, then definitely you can conserve the linear momentum of the system. Okay, so that's advantageous for us. The situation is, examiner says the man starts walking. Initially, system is at rest. Initially, system is at rest. Okay. When man starts walking, see, I'm writing the entire situation in front of you. When man starts walking with velocity u, over the boat, or with respect to boat, then they are asking you two things: the exact velocity of boat with respect to ground and the exact velocity of the man with respect to ground. All right, see, the situation is that this is m0 and the system was initially at rest. Now what happened? It started moving with velocity u with respect to boat. If it is moving over the boat, man is moving over the surface of boat, which means man's velocity will be attained with respect to boat. But now what they are asking is the exact velocity of the man with respect to ground, and or maybe the recoil velocity of the boat with respect to ground. Now can you feel that? If I try to represent the situation over here, I would say this is the man who is trying to move with some velocity in the forward direction. This is the V cap, and this is the boat. So why it is happening? Because if the man wants to walk forward, his legs, shoes will be moving backwards. So friction on his feet will be in forward direction, and friction over the surface of the boat will be in the backward direction. Once again, I am telling you, this friction is an external force acting on the man. So man's momentum will be changed. The same friction's reaction, this lower friction, is the external force acting on the boat. So boat's momentum will be changing. But if you consider man plus boat as a system, the same friction will become an internal force. And hence you can apply conservation of linear momentum, keeping the relative velocity in mind. And also, now you have to keep my shortcut in mind, that always take the opposite mass. Let us try to write the final answers in one shot, final answers in one step. See, what I'll say here is, I will be saying that velocity of boat with respect to ground. See, eventually the boat will be moving in the leftward direction. So recoil will be leftward minus, and always take the opposite mass. So if you are writing the velocity of the boat, whose mass is to be taken? Man's mass. So that is m0. Man's mass is m0 into relative velocity u by total mass of the system, m0 plus capital M. Once again, if examiner is asking you actual velocity of man with respect to ground. So actual velocity of man with respect to ground, effectively the man is moving in forward direction. If the man is moving in forward direction, then that will be plus. Always take the opposite mass. If you are writing the velocity of the man, then whose mass is to be taken? Opposite, boat's mass. So that is mass of boat, capital M, into relative velocity u by m0 plus capital M. Again, since you are writing the vectors, these negative and positive signs are only going to contribute in the directions, not in the magnitude. I hope it is clear for you. If you want, you can take it screenshot, Notes will be soon attached to the description of the video by the end of the day. And you should also, share these videos, share this bridge course to all of your friends, so that even if your friends and other students, other learners are sitting back at home, they can make a productive use of this time and can, keep learning a lot. All right. And education is something you should spread as much as possible. It's a good deal. All right. So take a screenshot. All right. I hope you understood the special emphasis on a two-particle system. We will keep talking about a lot of models, but the rule is, sir, that if the initial momentum of the system is 0, means initially system is at rest. You are talking about the two-particle system. There is no external force acting on the system. In that case, see here, the water will offer negligible friction. The water will offer negligible friction. As a result, you can conserve the linear momentum. The friction, this friction intermediate, the inner friction will be a considerable friction that will change the momentum of both individually. But for a system, that will become an internal force. So system's momentum will be still conserved. Hope that is clear. All right. Now, let me take you towards other models. Next is Seashore problem. Seashore problem. So one quick consideration is, again, illustration 1. In this illustration 1, this is a seashore. Okay. And at a distance of x0 over here, there is a boat. There is a boat of mass m, and its length is L. Its length is L, and there is a man of mass m0. This is the situation. This is the situation. Now, what is the initial separation? What is the initial separation of the man from the seashore? That is L plus x0. Examiner is asking, determine the final separation. Determine the final separation of man. Final separation of man from shore. From shore. Determine the final separation of man from shore when he comes to the other end of the boat. Other end of boat. All right. That is the problem statement. That there is a seashore over there, and I'll also take another illustration for your convenience. So, all right. So here, that's the seashore over there. X0 separation. There is a boat of mass m. Person is standing on one side of mass m0. Now the person starts walking on the other side. So if the boat is fixed, and the person walks on this end, then what will be its final separation? X0. All right. But the twist in the story is, the moment man starts walking on this side, the boat will also be shifted ahead. Recoil, the boat will be shifted ahead. So final separation will be definitely less than x0 plus L, but that will be still more than x0. The reason is in a later stage, when the man will be reaching at the other end, the boat will be somewhat like this. The boat would also be shifted here. When the man reaches this end, the boat is also shifted because of the recoil. Internal friction, just now I explained. All right. So system's momentum can still be conserved, and whatever pattern I have taught you, whatever things we have learned that always take the opposite mass in terms of velocities, the same pattern can be applied for the displacements. Whatever pattern of taking the opposite mass we have learned for velocity, exactly the same pattern can be applied for separations or displacement here. Otherwise, I can do it with a long way, but I want you to write all the answers in one step. All the answers in one step. So final answer directly we will write in one step or two steps here. How? So I hope you did understand that since the boat is also moving, the final separation will not be x0, it will be x0 plus something. It will be x0 plus something. So I will say here, the final separation of man, x final of man from shore, that will be equal to initial separation of man from shore. Initial separation of man from shore plus the displacement of man covered with respect to ground. Now, why you are adding this, sir? Because obviously I will add the displacement, since that will be happening in the negative left direction. I'll substitute it as minus. But logically what you need to understand is that I am standing over here. Now you will displace me somewhere. So my final separation or position vector will be initial position vector plus the displacement you have provided. All right. And why you have taken it with respect to ground, sir? Because seashore is on the ground. Twist in the story is what I explained earlier, that you have to consider the displacement with respect to ground. But what displacement you know is over the boat. The man has traveled an L distance over the boat. So that will be equal to the initial separation was x naught. The initial separation was x naught plus you are interested in writing the man's displacement with respect to ground. Since it is towards left, you will be writing it as minus. It is towards left, you will be writing it as minus. Now, whose displacement you are writing? Man's displacement. Always take the opposite mass. If you are taking the man's displacement, then whose mass is to be taken? The boat's mass. That is capital M into the relative displacement you have covered. The relative displacement you have traveled is L by M naught plus capital M. M naught plus capital M. I would like to emphasize on these points. This is because of left. This is mass of boat. Always take the opposite mass. And this is relative displacement. The pattern which you have talked in terms of velocity, the same pattern you can directly apply for displacement, and hence the final answer is, this implies the x final will be equal to x naught minus capital ML by M naught plus capital M. Capital ML by M naught plus capital M. This is going to be your final answer. I hope it is clear. All right. So it is all about when you are moving in this direction. Okay. Now, suppose I portray the same situation once again. There is a seashore. Let us modify a few things here. There is a boat. There is a boat of say 80 kgs, or say take it as 90 kgs, 90 kg boat, and there is a dog. Dog's mass is 10 kg. This distance is 5 meters, and this distance from here to here is 45 meters. This distance is 5 meters. The other distance from the initial distance from the shore is 45 meters. It's a two particle system, dog plus boat. Since it is over the surface of the water, there will be negligible friction offered by the surface of water, means there is no external force acting on the system as such. There will be no external force acting on the system. All right. Now, what you see over here is that the dog moves to the other end, and then you have to tell the final separation. But again, the issue is when the dog is moving towards this end, the boat will also be shifted a bit back like this. When the dog moves at the other end, the boat also shifts back. So the final separation will not be 45 plus 5, 50. The final separation will be somewhat lesser than 50. Somewhat lesser than 50. Now, how to get that? Let me solve this in front of you here. I will say the final separation of dog from the shore will be equal to the initial separation of the dog from the shore plus the displacement covered by the dog with respect to ground. Why with respect to ground, sir? Because obviously the seashore is a part of the ground or a part on the ground. So initial separation of the dog is 45 plus whose displacement you are writing? Dog's displacement. Since it is moving in the forward direction, it has to be positive over here. Now, if you are writing the dog's displacement, whose mass is to be taken? The boat's mass. So boat's mass is 90. Okay. Boat's mass is 90 into relative displacement. So the dog has moved over the boat a distance of 5 meters by total mass of the system. So that is 90 plus 10 like that. So that is 45 plus, if you see in the numerator, it is 9 5s of 45, 450. Okay. By 90 plus 10, it is 100. So you'll get 45 plus 4.5 and hence it is 49.5 meters. All right. So this is the final separation of the dog from the shore. Final separation of dog from shore. As you can see that we have got it as 49.5 meters. Is that clear? I hope you understood this model also. This model, we call it as Seashore model. Seashore model. The logic is very simple. Two particle system, very important for NEET. Two masses, binary star system, satellite and a planet, gravitation. Two charges, Coulomb's law, atom and nuclear, atomic structure, nucleus and electron, two particle system. Okay. So two particle system, two charges, two masses. The majority of physics for NEET syllabus is dealing with the two particle system. And today I have given you a very beautiful shortcut for the two particle system, that while applying the conservation of linear momentum of a two particle system, if the initially the system is at rest and obviously the external force acting on the system is zero, then writing the final results for the two particles in terms of the relative component, relative velocity of relative displacement, always take opposite mass. Always take opposite mass. That's what we have been doing here. Here also we have been doing the same. Here also we are doing the same. And here also I explained the relative motion model exactly the same. All right. So these are the problems. Today I haven't, I'm not discussing any different other problems for you. These are the situations which are the standard problems you might expect in the NEET exam. All right. Let me take another model, block over the wedge. Block over the wedge. So here, now let us consider, again I will consider this as illustration 1 here. This is wedge, okay, wedge inclined plane. This is mass capital M, and it is placed over a horizontal floor. And since we don't want any external force to be acting on the system, gravity will still act in vertical direction. So slowly you can't conserve the linear momentum. Suppose there is a block of mass m0 over here, which is released, and this angle is phi. Okay. This distance, this length is x. This length is x, and this length is y. So definitely the length of the inclined plane will be under root of x square plus y square. Pythagoras theorem. This will be the case. So y can be h, x can be the base length, okay. Y coordinate is the height. That can be in terms of different symbols, doesn't matter, okay. The ground is smooth. Naturally, gravity is acting in the vertical direction, sir. Gravity is acting in the vertical direction, so you can't conserve the linear momentum here throughout in the vertical. Gravity will influence the momentum of the block especially. But since horizontal, I want to conserve the linear momentum. So I'm telling you the standard case is that it is smooth, and this wedge is also smooth. This wedge is also smooth given to you. Okay. So the question is, determine the horizontal displacements, because you can't do that in the vertical, right? So determine the horizontal displacements of block and wedge when block reaches the bottom. So you have released it from there. Definitely every surface is smooth. So that will keep coming down, and it is not fixed. This is not fixed. This is movable. So if it is movable, by the time the block is coming down, the wedge will also be keep shifting left. The wedge will also be keep shifting left. So when block reaches the bottom, this is the question for us. Okay, that's the problem model. So what to do here? Again, it's very easy. Conservation of linear momentum. I will say here, conservation of linear momentum, or the shortcut technique that always take the opposite mass and all. Conservation of linear momentum can be applied only in x direction. Can be applied only in horizontal. Only in horizontal x direction. Okay, x axis. Why is that so, sir? Just now I have mentioned it multiple times that because in vertical direction gravity is acting, so you can't conserve the linear momentum in the vertical direction. You can do that in the horizontal direction. All right. Now let us see here. So I will say in this situation, velocity, if they are asking you not the velocity, the displacement of block with respect to ground, and obviously they can ask that in x-axis. The displacement of block with respect to ground, they can ask you that in x-axis. So that will be equal to, since the block will be shifted in the forward direction, so that should be positive. Now, if you are writing the displacement of the block, always take the opposite mass. Then you should be writing the mass of the wedge, capital M. You should be writing the mass of the wedge into the horizontal displacement traveled relatively. If it is horizontal displacement traveled relatively, then that horizontal displacement is x naught. That horizontal displacement is, let me take it as x naught over here. This is y naught and it is x naught square, y naught square. So it is opposite mass into relative displacement traveled horizontally by total mass of the system, that's m naught plus capital M. Similarly, if they are writing the displacement of wedge or inclined plane with respect to ground, then in the horizontal then obviously by the time block is sliding down, the wedge will be moving left. If the wedge will be moving left, I should be writing it as minus of, since you are writing the displacement of the wedge, take the opposite mass. The opposite mass is the mass of the block, m naught, into x naught, relative to each other will be x naught only, over m naught plus capital M. Relative motion obviously will be same but in opposite direction. I hope the logic is clear. Okay, let's take another example here. I would say that suppose this is the situation that this is a L length of inclined plane. This is m naught mass here. This is L length inclined plane. This angle is phi. This is capital M, and the situation is just the same. Problem statement is just the same, exactly same statement. All right. Here, this is also smooth and this is also smooth, so that there is no disturbance in any other direction because of the external forces. Vertical direction we can ignore because the examiner is asking you the displacements covered in horizontal direction. Once the block reaches the bottom, now if you want to write the final answers here, then the only difference between this problem and that problem is, here the base length was already given. Here the length of the inclined plane is given, so no issues. The base length over here can be written as L cos phi. The base length can be written as L cos phi. So if you are writing the displacement of the block with respect to ground, again it will be, once more, since it is in the forward direction, you should be writing it as positive and you are writing it in horizontal only. Or if you want me to write both of them, let me write both of them for you. So displacement of block with respect to ground in horizontal direction, x, that is equal to, since it is moving in the forward direction, it is positive. Always take the opposite mass, capital M, into relative displacement L cos phi by total mass of the system, m naught plus M. And not only that, dear, you will also write that the displacement of block with respect to ground in the vertical direction. Now you can't apply the conservation of momentum here. Because of gravity, but you can directly see that block is moving where with respect to ground in vertical. It is moving down. In vertical direction, and how much? L sin phi. This distance from here to here, I would say that this distance, y coordinate, will be equal to L sin phi. All right. So that will be equal to how much? Directly you will write minus because of down, and it is L sin phi. See, this plus means in horizontal direction it is towards right. This minus means that in vertical direction it is down. So even if they are asking you the net displacement, then that will be under root of sx square plus sy square. Similarly, if they are asking you in displacement of wedge with respect to ground in the x-axis, the displacement of wedge with respect to ground in the x-axis, that will be equal to, see, the wedge will be moving, the inclined will be moving in the left direction, so that is minus, always take the opposite mass, that is m naught into L cos phi by m naught plus m. And if they are asking you the displacement of wedge with respect to ground in y-axis, then that is equal to 0. Because wedge is not moving vertical. Wedge is not moving vertical. Block is moving horizontal also according to the shortcut technique of conservation of momentum. And block is moving in vertical also, which is given obviously minus L sin phi. Wedge is not at all moving. Inclined plane is not at all moving in vertical direction. It is just getting displaced in leftwards direction. So this negative is showing left. I hope the entire logic in front of you, that's clear to you. All right. So we have learned a very beautiful technique today. Make sure you revise everything before you sleep tonight. Our next interaction will also be based on conservation of momentum. But phase 2 means we will keep looking for a lot of other models and a bit of flavor of collisions also in conservation of momentum. A bit about it, not the detailed discussion. All right. That's all for today. That's all. Stay healthy, stay smiling, take care of yourself. COVID cases are increasing, so don't unnecessarily roam here and there. Stay back at home, prepare well, smile, laugh, and take care of your health. All right. All the best. Bye-bye. See you tomorrow.